For this first one, we're comparing the actual function at 1, the first derivative at 1, and the second derivative at 1. So f of 1 is 0. We have that point there, 1, 0. And then the first derivative at 1, first derivative tells us whether the function is increasing or decreasing. So since this function is increasing, I'll get out my stick it here. Since this function is increasing, that means that the first derivative is positive. So I don't know exactly what the value is, but I know that this is going to be positive. So it'll be bigger than 0. And then the second derivative at 1, the second derivative tells us about concavity. So this graph is concave down, it's bending downwards. And so concave down means that the second derivative is negative. So I don't know exactly what value the second derivative is, but I know that it's negative. So I know it's going to have to go negative and then 0 and then positive. So we want the second derivative to be smaller than just f of 1, and then that's smaller than f prime of 1. So that one is going to be b. All right, so number 2, graph of the derivative of a function is shown. The domain is from 0 to d. Which of the following statements is true? So I'm going to pull out my stick-it note here. So we have a local minimum at C. Well, no, that can't be true. Minimum would mean a change from negative to positive, and at C, we're changing from positive to negative. So there would be a maximum at C. So it can't be that one. All right, maximum at B. Well, B isn't even a critical point. It's not even touching 0 there for the derivative, so it can't be that. Point of inflection at A, f of A. So for f prime, a point of inflection is going to be when f changes concavity. So that's going to be when f prime, which is what we have, changes from increasing to decreasing or decreasing to increasing. And that's not happening at A. It's not changing from going up to going down or vice versa. So it can't be that one. And then D, point of inflection at B, f of B. So that's going to be this point right here, and that's going to be the one that's true. We have a change from increasing to decreasing. So that means that the graph of f changed from concave up to concave down, and that means point of inflection. So that one's B. Let's look at E real quick as well. It says f is concave up from C to D. Well, from C to D, the first derivative is negative. It's below sea level. Or I'm sorry, I guess we don't need to look at positive and negative. We need to look at increasing and decreasing. From C to D, the derivative is decreasing, going downwards, and decreasing means concave down, and this says concave up, so that is why it's not E. All right, I'm sorry that these other graphs didn't show up when I printed this. I did fix it so they're showing up when you get this, on Schoology. So you were able to see all of them on Schoology. I didn't print it again because the answer is one of the ones that's shown, and I wanted to save paper here. F is shown in the figure. We want to graph the derivative of F. So these would be our critical points. This is where we're having a slope of 0. So at these 3 values, at A, and then kind of at like a little bit above 0, and then at B. And then this graph is increasing and then decreasing. So for my derivative, I want to be above and then below. So increasing means derivative is positive, decreasing means derivative is negative. And so that one is A. All right, for number 4, at which of the 5 points on the graph are the first derivative and the second derivative both negative? So if the first derivative is negative, that means that the graph should be decreasing. If first derivative is negative, that means the graph should be decreasing. And if the second derivative is negative, that means that the graph should be concave down. So we're looking for a point where the graph is decreasing and concave down, and that's happening at B. All right, and then number 5, it says let f be a polynomial function. All right, so polynomials are continuous and differentiable. So even though they didn't say that, we get to know that this function is continuous and differentiable since it's a polynomial. And we're given all these points. It says, which of the following has to be true? All right, what I would do is just go ahead and plot these just to get a visual of this. We've got -2, 3, 0, 1, 3, 4, 5, 7, and 6, 5. And so we're going to look through and see which one of these is true. So letter A, the graph of f is concave up. All right, concave up would be when the derivative is increasing. These are values for the derivative as well. This is f prime. So concave up would be when the derivative is increasing. Well, this graph would not always be increasing. To start out, it would be decreasing to get from here to here. So it cannot be A. B, the graph has at least 2 points of inflection. So again, point of inflection is a change in concavity. That would be where f prime changes from increasing to decreasing or vice versa. And if we were to connect these, there's going to be at least 2 places where we have a change from decreasing to increasing or increasing to decreasing. So it's going to have to be B. We're going to have at least 2 points of inflection. It could, change direction more often in between those points. I don't know exactly what it's doing in between, but we'll have at least 2. Let me look through the other choices as well. C says function is increasing. That would be when the derivative is positive. Now, the way I drew this, it looks like this is always going to be above sea level. But again, we don't know what happens in between these points. And this could come down here before it connects to the other point. We don't know. So it could go negative. So we don't know. So it can't be C. F has no critical points. Well, again, this could come down here and go through 0, and we could get critical points. The way I have it drawn right now, there wouldn't be any critical points. But like I said, the graph could do something like this, and then you would have critical points. So it's not D. And at least 2 relative extremes, maximums and minimums. Well, again, if it was graphed like this, we don't have any critical points, and so you wouldn't get any relative maximums and minimums. So you can't be guaranteed at least 2 of them. You might not have any at all, so it can't be E. All right, number 6, we're given all these charts of values. We are told that the function has a positive first derivative. So first derivative is positive. That means the function should be increasing. And it says a negative second derivative. So second derivative is negative. That means concave down. So first, let's look at increasing. We can eliminate several choices because the values aren't increasing. If you look at C, let me zoom in. If you look at C, the values go 16, 12, 9, 7. So those are not increasing. D is not increasing, and E is not increasing. So you've narrowed it down to 50-50 chance here. Concave down. So if this graph is increasing and concave down, it's going to do something like that. So it's increasing quite a lot. If I draw in tangent lines, this would be a really steep slope, and then it's not quite as much. So we want to be increasing, but by a less and less amount each time. That's kind of what causes it to be concave down. So we want to increase, but by a lesser and lesser amount as we go on. So if you look at A, to get from 7 to 9, we added 2. To get from 9 to 12, we added 3. And to get from 12 to 16, we added 4. So we're increasing by an increasing amount. It's going up more and more each time. That would make it concave up. That would do something like this. Like it would increase and then it would go up more and more and more each time. So it's going to have to be B. To get from 7 to 11, that's an increase of 4. From 11 to 14 is an increase of 3, and from 14 to 16 is an increase of 2. So you're still increasing each time, but by a less and less amount. All right, so number 7, we're given the graph of f. So this is not f prime, this is just the graph of a function f. For which of the following values is f prime positive and increasing? Right, let me get out my sticky note. If f prime is positive, that means that the graph should be increasing. So we want to pick a point where the graph is increasing. And if f prime is increasing, that means the graph should be concave up. If f prime is increasing, concave up. So we want to pick a point where we are increasing and concave up, and that's going to happen at E. All right, number 8, this is non-calculator. I just don't want you guys to throw this in your calculator. This would be non-calculator on the AP exam. Right, it says, which of the following statements about this function is true? And then they start talking about relative maximums and minimums and inflection points. So we're going to need to look at the first derivative and the second derivative. All right, so first derivative would be 4x cubed minus 6x squared. I'm going to set that equal to 0. So we would factor out 2x squared, and we would be left with 2x minus 3. Now, I'm not going to actually make number lines. We'll just kind of talk through this. If I made a number line for 2x squared, it would be positive all the time. If you square something, it is always going to be positive. So we will not get a relative maximum or minimum out of that because there's not going to be any change. So this one does not give us a relative extrema. This one, we would have a change at 3/2 from negative to positive. So you're going to get a relative minimum at 3/2. All right, so that's first derivative. Now let's get the second derivative. So I'm going to take the derivative of this. That would be 12x squared minus 12x. And so we're going to factor out 12x, be left with x minus 1. And so if you made number lines for each of these, this one would have a change at 0, and this one would have a change at 1. So you would end up with 2 inflection points. So we got 1 relative extrema and 2 inflection points. Let me see which one says that. That one is C. All right, number 9, let f be a function defined and continuous from A to B. We have a relative maximum at C, and C is in between A and B. Let me draw a visual for that. Here's A, here's B. They're saying C is somewhere in between, and we have a relative maximum there. All right, so Roman numeral 1, the derivative at C exists. That might not be true. What if you had an absolute value function? What if you had this? You would still get a relative maximum there, but you wouldn't be differentiable due to the sharp edge. So maybe not. Remember, critical points are where the derivative is 0 or undefined. So the derivative doesn't necessarily need to exist. You can have a sharp edge. All right, Roman numeral 2, if the derivative does exist, then it equals 0. Now that's going to have to be true. If we have a relative maximum at C, and we can get a derivative, like it's not a sharp edge, that derivative would have to be 0. So Roman numeral 2 is going to be true. And then lastly, if the derivative exists, then the second derivative is less than 0. That means negative. Second derivative being negative means concave down. And that's also going to have to be true. If we get a maximum there, this graph has to be concave down to make that be at the top of the hill. So that one is also going to be true, and so we get E for that one. And then last one, we're picking which graph this is going to be. We have the function itself, the first derivative and the second derivative are all negative. Okay, so let's go through those one at a time. First, f of x. If f of x is negative, it needs to be below the x-axis. If the function itself is negative, that means it needs to live below sea level. So A is okay, B is okay, C is okay, D is okay, E is a problem. It cannot be E. That one is above the x-axis. Right? If the derivative, the first derivative is negative, that means the function should be decreasing. So it cannot be A, that increases and then decreases. B is okay, that one's decreasing. C is increasing, so it can't be that. And D is decreasing, so that's okay. So we've narrowed it down to B and D. And if the second derivative is negative, that means concave down. So out of the two choices that are left, we want one that's concave down. And so that is going to be B. This one is bending downwards. It looks like D is concave down and then changes to concave up. So you would have, a point of inflection right about there. You would be, concave down and then change to concave up. So it cannot be that one.